Right. So longevity dictates that you want to be doing what's necessary to signal your body to enter into that reparative mode, right? And that's at odds with when you're younger, you want performance gains. If you're an athlete, you want to build, big muscles and all of these things. That's all fine, but you can't have both.
It's very hard, I would say, and people who are who grow fast have to be extra cautious because their bodies, especially when they're young, are spending more of their energy on growing than hunkering down. Uh-huh. And this is just a fact, but it's probably depressing to some people that, at least in dogs, and it looks also like in humans, that if you've got a highly active growth system, a lot of growth hormone, it will work against you later in life.
Yeah. Mm-hmm.
Yeah. But, again, a lot of it's in the control of our environment. If you're a tall person, I'm not, but if you're super tall, I think it's even more important to make sure that what you eat and how you fast and how you exercise is optimal if you want to live the maximum potential lifespan.
I have a lot of friends who get testosterone therapy and can get, HGH and all of these sort of things. And the idea is it's boosting their, virility and their energy levels and all of that. But I can't help but wonder what the implications are on their long-term wellness and well-being and longevity. Like there's a evolutionary rationale why these things decline over age, right?
Well, you could say the same about NAD, that it declines and it's not good to boost it. So I think that's dangerous to use that argument, that just because something goes down, it's meant to. Uh-huh. But there have been millions of dollars poured into clinical studies with testosterone with no benefit to health span and I believe lifespan as well. And so in our field, we actually regard those studies as somewhat of a failure to deliver. And so I think that the evidence is there that it will give you, testosterone probably gives you great benefits. If you're exercising, you can build up more muscle, you're more quote unquote virile. But in the long run, it doesn't help you and probably hurts you.
Because it's signaling your body that it doesn't need to produce it on its own? Or because it's stimulating growth in areas that you don't want growth?
That would be my explanation. I don't know for sure, but I think just telling the body grow, build muscle all the time is basically sending the wrong message for a long lifespan.
Right. What about exercise? What's happening when we exercise, and how is that impacting aging, longevity?
Well, first of all, let me tell you what exercise isn't. It's not just making your blood flow around your pipes and cleaning them out. That's what I was led to believe in the 1970s. What's actually going on majorly is two things. One is it's activating these longevity pathways in your bloodstream, and I've mentioned earlier that the sirtuins are a major part of that. But it's also having highly anti-inflammatory effects, and it's able to change the way our bodies actually respond to the environment. Exercise is a treatment for the body that actually puts the entire system in a state of defense, and so it's less about getting the blood to flow and more about getting your tissues to act younger. Mm-hmm. And that's really the huge benefit that you get from exercise.
So why can't we diet and exercise ourselves into immortality?
Yeah, that's a good question. Because I think that these defense pathways are not perfect. They don't know how to fully reverse the scratches, polish off the scratches on the CD. Sure, they can slow them down, but as we lose our epigenetic information, our ability to read the right genes at the right time, that's beyond the expectations of the sirtuins and mTOR. We need something more potent to really reset the body's clock. Now, the body's clock, we actually understand a lot more about that now. We can read that clock in our blood and in our tissues, and it's at the level of the genome and the changes to the genome. We've been working on ways to actually literally reset that clock. Mm-hmm. And that would be the way to not just live an extra 5 or 10 years in a healthy way, but potentially take a 90, 100-year-old and make them feel decades younger pretty quickly.
Wow. So what are the big questions that you're wrestling with right now that you're trying to get answered? And what would be the studies that you would like to see conducted, the research, in your perfect world that would help you make the breakthroughs that, you're attempting to make in this world?
Well, the hot area now, as the NAD boosters move into drug development, so that's on its way. What's coming down the line that isn't well known is called cellular reprogramming. This is truly resetting that epigenome. What it is, it's essentially telling the cell, can you go and find the information that once existed when you were young and ignore all the other information that's accumulated over time? We call this epigenetic noise in my lab. It's a term that we've had to coin because we've run out of vocabulary. So epigenetic noise, as I mentioned, is caused by mostly DNA breaks and other things that occur to us. But how do you say to the cell, your DNA should be wrapped up in those histone proteins this way and just ignore all those other changes that have occurred? So we think we've found a way, at least early days. I don't know if you and your listeners are familiar with the pluripotent stem cell technology, where you can take a skin cell and turn it into a stem cell.
No, explain that.
Yeah, so there's a famous scientist called Shinya Yamanaka, and he won the Nobel Prize in 2012. And what he found was that by turning on 4 genes in cells, and they can be hair cells, skin cells, liver cells, he can take an adult cell and make it super young again, so that it now is what we call a pluripotent stem cell. We call them IPS for short. Those can be made into any other cell type, such as an egg or a liver cell.
Whoa. So you could literally take any human cell, pull a strand of hair, extract a cell, activate those 4 genes, and end up with this stem cell.
Well, not only can you, we all do it now. It's commonplace. Every graduate student typically works on this stuff. So it's commonplace. But the trick is, how do you use that technology for human health? And we're just learning how to do that now. But what's crazy is, so I could take your skin cell and I could make a sperm out of it. I could make an egg out of it, and I could make a new you that way. It's crazy stuff.
That's crazy.
But it's doable. But getting back to aging, what does that mean? Well, what we decided to do with some other colleagues who are also in this field, is about 4 of us, turn on those Yamanaka factors, as we call them, those reset genes, not in a cell in the dish, but in an animal and maybe one day a human. Because maybe we could use them to partially reset the age of a cell. We don't want to go all the way back to beginnings. We don't want to turn us into a stem cell. That would be the end of us. We'd be a giant teratoma or a giant cancer tumor. But if we could just do a little bit, just pulse the body so that it goes back to its earlier age, that would be the Big Bang in biology.
That's just straight up out of a science fiction movie.
Well, that's what a lot of us thought.
Your face just lit up like a Christmas tree, though. Like, this is definitely what gets you excited.
Well, it does. And it did sound like science fiction. And that's why it took me a couple of years to convince my students to work on it, because they thought it was crazy and it would be impossible. But then there was a study that came out from the Salk Institute down in San Diego from Juan Carlos Belmonte's lab. And he did that crazy experiment before we had a chance to do it. He gets full credit. What he did was he made a mouse that he could turn on these 4 Yamanaka genes in the animal once it was an adult and ask what happens. And what happened was, after 2 days, the mice died. Okay, that's not going to win you a Nobel Prize.
Yeah, that's not a good start.
That's a bad day for the mouse especially. But what he figured out was that if he switched the system off on that second day, the mice were fine. Well, they recovered, but they ended up being much healthier. And he did this in what we call a progeroid mouse model, but that just means a mouse that ages rapidly. It's the same essential mouse that you can find those young patients who age prematurely, right? The poor kids that get old when they're 13. Mm-hmm. There's a mouse that is a model for that disease. So the Belmonte lab, they turn on these genes every 2 days out of a week. And then, it's every 2 days, and then they wait another 2 days and they turn them on again. Those mice live 30 to 40% longer.
Wow. So it's sort of like they're getting pulsed with it.
Right. So the argument, if you want to criticize the work, and a lot of people have, is that they're just making the mice sick, and it's a form of hormesis. But I didn't think that was true, because we've been working on this reset button for ages, and we thought that was probably the secret. And one of the things we did was we had tried a whole bunch of genes for resetting, and they didn't work. But now we saw that those Yamanaka factors could be important. And so what we did was first of all, we wanted to figure out, why are they toxic? Why is it hurting the animals? And so we left off one of the genes that was really toxic. It's called MYC. And MYC is already known to be a cancer-causing gene, so that didn't take a genius. But when we put in 3 out of those 4 genes, turns out that the mice are perfectly fine. They don't get sick. We've now put it into mice, and they're perfectly fine. But what we're seeing is evidence of regeneration and age reversal in those old mice.
And because you're seeing it in mice, what does that mean in terms of human health? Like, is this, granted, it's not a 1-to-1 ratio, because you see a 30 to 40% increase in lifespan in a mouse doesn't mean that's going to work in humans. Like, what are the similarities and differences when we move, up the food chain to more complex organisms?
Yeah, right. So it's fair to say that we've cured cancer in mice 1,000 times over. It's a lot easier to do things in mice for some reason. Extending lifespan in mice may be much easier because they only live a few years, whereas we live 80 on average. But these fundamental mechanisms that I'm describing today are found in everything from a yeast cell to a plant, many animals, mice, of course, and us. So these aren't just some esoteric pathway. These are fundamental mechanisms of living things. So my philosophy is that as long as we don't do any harm, there's a very good chance that what we can do in a yeast cell, a worm, and a mouse will also work in a human, because a yeast to a mouse is 99.9% of the way there. It's just that little bit of extra difference. But if you ask a yeast cell, we're basically a giant mouse.
Wow. So in your lifetime, our lifetime, well, I guess we should say, I don't know what lifetime means given the work that you're doing. Lifetime doesn't mean what it would normally mean, I suppose. But rationally or realistically or reasonably, given your aspirations, where do you think you will see all of this in, 40 to 50 years from now, like during our typical lifespan?
Yeah, what's a typical lifespan? It's hard to see where the world's going by looking backwards. In 1902, would we have predicted that we'd be flying jumbo jets and flying to the moon? I don't think going to the moon.
We're pretty terrible at predicting.
We're really bad.
Future outcomes.
So Arthur C. Clarke said it's a very dangerous profession that he was into, predicting the future. But I'm happy to do it. There's no harm in trying to see what the future looks like. And I have a front row seat, so I'm partially qualified to make these guesses. So what I see for the future is, first of all, that there are 2 futures. One is if no aging research is successful, what does the world look like? And that's a world that's still pretty good, but it's not great. Pretty good in the sense that the trajectory is that a child born today in the US will expect to live to 104. Remember that this child is going to see the 22nd century. What great things will be available for them? Who knows? But even if we don't do anything, we're going to have longer lifespans. By the way, in Japan, it's 107. So it's not crazy to say that people will be living